Start, man.
Good morning, one and all. Myself Swapna, JL Chemistry from Vangara. Before entering into the lesson, first of all, I will appreciate the D Durga, P Prasuna, T Pujita, A Anoja, V Srilata. Number of students sent their assignment. But Durga belongs to Hasanparthi. She sent her assignment and as well as running notes as PDF. Very good, Nana. Keep it up. All the best. Do hard work and get more marks. Now, let us discuss. In this before class, we will discuss the hybridization and types of hybridization and bond parameters, dipole moment. Now we will discuss molecular orbital theory. This theory was developed by Hunna and Mulliken. The atomic orbitals have same energy or nearly same energy and proper symmetry combined to form molecular orbitals. That means the molecular orbitals are formed by linear combination of atomic orbitals of same or nearly same energies. This theory is explained by LCAO method. LCAO is nothing but linear combination of atomic orbitals. When two atomic orbitals combine to form two molecular orbitals, those are bonding molecular orbital and next one is anti-bonding molecular orbitals. This is a molecular orbitals. These are atomic orbitals combined to form molecular orbitals. This is the anti-bonding molecular orbital and this is bonding molecular orbital. What are the bonding molecular orbitals? The molecular orbitals formed by additive effect or constructive interference of atomic orbitals are called bonding molecular orbitals. The molecular orbitals formed by subtractive effect or distractive interference of atomic orbitals are called anti-bonding molecular orbitals. Here, the bonding molecular orbitals has less energy and greater stability. So these are represented by the sigma and pi. The anti-bonding molecular orbitals have high energy and lesser stability, and these are represented by the sigma star and pi star. These are the atomic orbitals. These atomic orbitals undergoes to forms these molecular orbitals. These molecular orbitals are bonding molecular orbitals and anti-bonding molecular orbitals. Here the bonding molecular orbitals have less energy and greater stability. These are denoted with the sigma and pi. These are anti-bonding molecular orbitals. Anti-bonding molecular orbitals have higher energy and lesser stability. These are represented with the sigma star and pi star. In this, the number of molecular orbitals are formed are equal to the number of combining atomic orbitals. Okay, that means in this, the number of molecular orbitals are formed are equal to the number of combining atomic orbitals, and the electrons of an atoms present in atomic orbitals, whereas the electrons of molecules present in these molecular orbitals. Order of molecular orbitals. Anti-bonding molecular orbitals. Anti-bonding molecular orbitals have higher energy and lesser stability than non-bonding molecular orbitals. Then non-bonding molecular orbitals have higher energy and lesser stability than bonding molecular orbitals. The bonding molecular orbitals has lesser energy and greater stability. The molecular orbitals like atomic orbitals are filled in accordance nature of the molecule, and it is used to calculate the bond order. How to calculate the bond order? The bond order is equal to the number of electrons the number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital by 2. It is also written as Nb minus Na by 2. Nb is nothing but number of electrons in bonding molecular orbitals. Na is nothing but number of electrons in anti-bonding molecular orbitals by 2. Then we will get bond order. Then how to write the electronic configuration of the molecules? Okay, the electronic configuration of molecules contain 14 electrons or more than 14 electrons. For example, oxygen and fluorine, etc. molecules. Because of this, oxygen molecules has greater than 14 electrons. Same as well, fluorine molecule also have greater than 14 electrons. So the electronic configuration of molecules contains 14 electrons or more than 14 electrons. Then you will write the electronic configuration of like this. First of all, the electrons entered into sigma 1s orbitals, next entered into sigma star 1s orbital, next sigma 2s orbital, next sigma star 2s orbitals, next electron is entered into sigma 2pz orbital, and next entered into pi 2px, pi 2py orbitals. These are degenerate orbitals. And next electron enter into pi star 2px and pi star 2py orbitals. These are also degenerate orbitals. And next electron is entered into sigma star 2pz orbitals. Here, this is the sigma star 1s orbital, and here it is also sigma star 2s orbitals. And here pi star 2px, pi star 2py, and sigma star 2pz. These all are anti-bonding molecular orbitals. The remaining are bonding molecular orbitals. The electronic configuration of molecules contain less than 14 electrons. For example, lithium molecule, beryllium molecule, and boron, carbon, and nitrogen molecules. How to write the electronic configuration? The molecules contain less than 14 electrons. In this, the electron is entered into first sigma 1s orbital, next electron entered into sigma star 1s, next electron entered into sigma 2s, next sigma star 2s. Then now here the electron is entered into pi 2px orbital and pi 2py orbital. The next electron is entered into sigma 2pz orbital. The next goes to pi star 2px orbital and pi star 2py orbitals. Next electron is entered into sigma star 2pz orbitals. And also how to find the HOMO and LUMO. What is HOMO? HOMO is nothing but highest occupied molecular orbital. HOMO is nothing but highest occupied molecular orbitals. It has electrons. Okay. HOMO means highest occupied molecular orbital. It has electrons. LUMO is nothing but lowest unoccupied molecular orbital. That means it is the next highest energy orbital. It is an empty orbital. That means it does not has any electrons. So it is HOMO and it is a LUMO. Now, how to write the MOED of H2? So here the H2 molecule is formed by the combination of two hydrogen atoms. We know that, yes. Yes, this hydrogen atomic number is 1 and its electronic configuration is 1s1. But here the hydrogen atom has 1 electrons. Then here the H2 molecule has 2 electrons. Because of this, H2 molecule is formed by the combination of two hydrogen atoms. So its electronic configuration is sigma 1s2. Now you fill these orbitals. Here these all atomic orbitals of hydrogen atoms, and these are molecular orbitals of hydrogen molecule. Okay. Then now here one hydrogen electronic configuration is 1s1. So you fill the electron in 1s orbitals. This is another hydrogen atom. Okay. These are combined to forms the molecular orbitals by LCAO method. These are molecular orbitals. Now you fill the electrons in molecular orbitals. In this H2 molecule, the electronic configuration is sigma 1s2. That means these two electrons first of all entered into the bonding molecular orbital. Okay, after the filling this bonding molecular orbital, any electrons if in these atoms, then electrons enter into anti-bonding molecular orbitals. So this is the MOED. MOED is nothing but mm, molecular orbital energy level diagram. This is the molecular orbital energy level diagram of H2 molecule. And this MOT theory is also used to calculate the bond order. Okay, and used to determine the diamagnetic nature. Yes, here bond order. Bond order is equal to Nb minus Na. Nb is nothing but number of electrons in bonding molecular orbital, and Na is nothing but number of electrons in anti-bonding molecular orbital. So you will substitute these electrons in place of these by 2. Then here in this helium molecule, in this H2 molecule, then how many electrons are present in this bonding molecular orbital? 2 electrons. So now we will substitute 2 electrons in this place of Nb. Then in anti-bonding molecular orbitals, it does not have any electrons. So you will put 0 by 2, then is equal to 1. So now bond order of hydrogen is 1. That means in these hydrogen molecules, 2 hydrogen atoms bonded through a one single bond. Okay, the next goes to, it is exhibit the diamagnetic nature because of it does not have any unpaired of electrons, because of due to the absence of unpaired electrons, these molecular orbitals are filled with electrons. In this in this diamagnetic nature, don't consider the electrons present in atoms, just you consider the electrons present in molecules. Yes, okay, then it is exhibit the diamagnetic nature due to the absence of unpaired electrons, because of in this the electrons are totally paired. Okay, in this the orbitals are paired with electrons. Diamagnetic means the molecular orbital, the atomic orbitals are fulfilled with the, and that means paired up with the electrons, then such type of atoms or molecules are exhibit the diamagnetic. So it is totally, this orbital is fulfilled with these 2 electrons. That is the reason it exhibit the diamagnetic nature. Next goes to mode of B2. Okay, mode means molecular orbital energy level diagram of B2. Then B2 molecule is formed by the combination of 2 boron atoms. Here boron atomic number is 5. Its electronic configuration is 1s2, 2s2 and 2p1. So now you will write the boron molecule electronic configuration. The boron molecule electronic configuration is 1s2, sigma 1s2 and sigma star 1s2, sigma 2s2 and sigma star 2s2, pi 2px1 and then pi 2py1. Because of these are degenerate orbitals. So that is the reason. Then you will first of all electrons you put in pi 2px, then pi 2py. Okay. Then these are the atomic orbitals of 2 boron atoms. These are the atomic orbitals of 2 boron atoms. These are combined to form the molecular orbitals. Okay, these are molecular orbitals. Now you fill the electrons. In the first of all, you fill the electrons in atomic orbitals of boron here and here. Here it is the 1s2 and 2s2 and 2p1. It is the one boron atom electronic configuration, and this is the another boron atom electronic configuration. Here also 1s2, 2s2 and 2p1. Then next you fill the electrons in molecular orbitals. First of all you fill the electrons in bonding of the 1 sigma 1s orbital. Next the electrons entered into sigma star 1s orbitals. Because of these in these atomic orbitals, in 1s orbitals 4 electrons are there, so these 4 electrons First of all, 2 electrons comes to the bonding molecular orbital. Then next entered into anti-bonding molecular orbital. Same as usual in this one also. Here, these 2s orbitals of electrons entered into, first of all, bonding molecular orbitals. The next entered into anti-bonding molecular orbitals. The next in these p orbitals, it is the 2p1 and it is also 2p1 of the atomic orbitals. Then these are entered into pi 2px and pi 2py. These are entered into, first of all, pi 2px and pi 2py. Then now you will write the bond order. This is the MOED of B2 molecule. Then now you will write the bond order. In this, the bond order is equal to NB minus Na by 2. Okay. Then NB is nothing but the electrons present in bonding molecular orbital. These are bonding molecular orbitals. In this, how many bonding molecular electrons are present? Here. These are bonding molecular by here 2 electrons and here also 2 electrons and here also 2 electrons. Total 6 bonding electrons are there. So 6 minus how many anti-bonding molecular orbital of electrons here? Here 2 electrons and here also 2 electrons. Okay. Then 6 minus 4 by 2, that is equal to 1. So here the bond order of B2 molecule is 1. That means B2 molecule is combined by the 2 boron atoms with one bond, with single bond. Then now it exhibits the paramagnetic nature because of it has unpaired electrons in its molecular orbitals. Because of it has unpaired electrons. These electrons are not paired up. That is the reason the boron molecule exhibit the paramagnetic nature. Next goes to mode of N2 molecule. The N2 molecule is formed by the 2 nitrogen atoms. Okay, the nitrogen atomic number is 7. Its electronic configuration is 1s2, 2s2, 2p3. Then now you will write the electronic configuration of the molecules. Actually, the nitrogen has 7 electrons. So now here the nitrogen molecule has 14 electrons. Then you will write the 14 electrons in this manner. First of all, write the sigma 1s2 and sigma star 1s2, sigma 2s2, and next electron entered into sigma star 2s. Next goes to pi 2px 2 and pi 2py2. Then next electron is entered into sigma 2pz orbitals. Then this is the MOED of N2 molecules. Okay. Then these are the atomic orbitals of nitrogen atoms. This is also atomic orbitals of one nitrogen atom, and these are also atomic orbitals of another nitrogen atoms combined to forms the molecular orbitals. Okay. Here one nitrogen electronic configuration is 1s2, 2s2 and 2p3. Here also another nitrogen atom electronic configuration is 1s2, 2s2 and 2p3. Now you fill these molecular orbitals. Here it has 4 electrons. So of these 4 electrons, the first 2 electrons entered into bonding molecular orbital. Next electrons are entered into anti-bonding molecular orbitals of the sigma star 1s. In these also 2 electrons are entered into bonding molecular orbital of the sigma 2s. Next 2 electrons are entered into sigma star 2s of anti-bonding molecular orbitals. Then in these 3 electrons, one electron is entered into, first of all, pi 2py and then pi 2pz. The next electrons are entered into sigma 2px. Then this is the MOED of N2 molecule. Then bond order. The bond order is equal to NB minus Na by 2. Here NB is nothing but number of electrons present in bonding molecular orbitals. Then how many electrons are there in this bonding molecular orbitals? You will count. Here 2 electrons and 2, and here 4 plus 2 6, and 6 plus 2 8, 8 plus 2 10, 10. And antibonding, the number of NM nothing but a number of electrons present in antibonding molecular orbitals. Antibonding means star, sigma star or pi star orbitals are antibonding molecular orbitals. Now here in this sigma star 2s has 2 electrons, and sigma star 1s 2 electrons. So total 4 electrons. So 10 minus 4 by 2, that is equal to 3. Then the bond order of nitrogen molecule is 3. That means in this nitrogen molecules, 2 nitrogens are combined through the triple bond. That is a bond order. Okay, bond order is nothing but a number of bonds between two atoms in a molecule. Okay, then it is exhibit the diamagnetic nature because of due to the absence of unpaired electrons in its molecular orbitals. Now you will if you will observe these molecular orbitals, total orbitals are completely filled with electrons. That means it does not have any unpaired of electrons in its molecular orbitals. That is the reason the N2 molecule exhibit the diamagnetic nature. Next goes to mode of O2 molecule. This O2 molecule is formed by the combination of two oxygen atoms. Here the oxygen atomic number is 8, electronic configuration is 1s2, 2s2 and 2p4. Then it has 8 electrons, okay? And that means its atomic number is 8. But what about the O2 molecule? It has 16 electrons. These 16 electrons you will fill these electronic configuration like this. First of all, the electrons entered into sigma 1s2, next entered into sigma star 1s, next sigma 2s, and next sigma star 2s, next sigma 2pz, next pi 2px2, and pi 2py2, and then pi star 2px1, and pi star 2py1. Here. These are the atomic orbitals of oxygen. Here, these are also atomic orbitals of oxygen. One oxygen electronic configuration is 1s2 and 2s2 and 2p4. Another oxygen electronic configuration 1s2, 2s2 and 2p4. Now, these electrons of the 1s orbitals, these electrons of the 1s orbitals, two electrons first of all entered into the bonding molecular orbital of sigma 1s, and next two electrons are entered into sigma star 2s, that is the antibonding molecular orbitals. Next in the 2s orbitals, the two electrons first of all entered into sigma 2s orbitals, that is bonding molecular orbitals, and next electrons are entered into sigma star 2s, that is the antibonding molecular orbital. And next in these, the 2p orbitals, these 2p orbitals of the electrons of two electrons first of all entered into sigma 2pz, sigma 2pz orbitals, and next entered into pi 2px and pi 2py orbitals. These are bonding molecular orbitals. Next you will write the bond order. Okay, the bond order is equal to, here how many electrons are present in this bonding molecular orbitals? You will count here 2 electrons, and here 2, and here also 2, 4, and 4 plus 2 6, and 6 plus 2 8, and 8 plus here these are two, total 10 electrons. Okay, and 10 minus electrons present in antibonding molecular orbitals, and 10 minus 6, that is by 2 is equal to 2. That means the bond order of O2 molecule is 2. Here the O2 molecule is combined with the two oxygen atoms through the double bond. Bond order is nothing but a number of bonds between two atoms in a molecule. And also this molecule is exhibit the paramagnetic nature due to the unpaired electrons. Here in this molecular orbital of oxygen molecule, it has two unpaired electrons. That is the reason it exhibits the paramagnetic nature. The next goes to MOED of He2 plus ion and He ion. Then now here, actually The helium atomic number is 2 and its electronic configuration is 1s2. Then these are atomic orbitals of the helium and these are molecular orbitals of the helium. So these two electrons first of all entering into the sigma 1s bonding molecular orbitals, and next these two electrons are entered into the sigma star 1s anti-bonding molecular orbitals. Now its bond order is equal to 0 because of bond order is equal to Nb minus Na. Here, how many electrons are present in this bonding molecular orbital? 2. So you will write 2 minus how many electrons present in anti-bonding molecular orbital? 2. So 2 minus 2 is equal to 0. So here no bond order. The next goes to He2 plus ion. Okay, then He2 plus ion is nothing but it lost one electron. Okay, actually the helium has how many electrons? 4 electrons. Of these 4 electrons it lost its one electron because of it has one positive charge. Positive charge is nothing but losing of electrons. It has only one positive charge, so that it lost its one electron. So now another one helium atomic number is 2, its electronic configuration is 1s2, and another helium it lost one electron, so that its electronic configuration is 1s1, and these are the molecular orbitals of this helium molecule. Then now these two electrons first of all entered into the 1s orbital of bonding molecular, and next one electron is entered into sigma star 1s anti-bonding molecular orbitals. Okay, then now here this molecule is exhibit the paramagnetic nature because of it has one unpaired of electrons in its molecular orbitals. But in this helium, it exhibit the diamagnetic in nature because of it does not have any unpaired of electrons in its molecular orbitals. So from this in this chapter, we will discuss from starting to till now Cosell and Lewis approach to chemical bonding. Cosell-Lewis approach to chemical bonding. It explained the what are valence electrons and core electrons and which atoms try to get inert gas configuration. And next goes to we discuss the octet rule and its limitations. And next we discuss the Lewis representation of simple molecules. I explained the how to draw the Lewis dot structures of some atoms and some polyatomic molecules, and types of chemical bonding. The types of chemical bonding. These are we discussed 4 types. Those are ionic bond, covalent bond, coordinate bond, and hydrogen bond. Ionic bond, covalent bond, and coordinate bond. These are strong bonds because of they have strong force of attractions. And hydrogen bond, fourth one is the hydrogen bond. It is a weak bond because of it has a weak force of attractions. Okay, and these ionic bond, covalent bond, and coordinate covalent bond, in these 3 type of bonds electrons are participated, but in hydrogen bond electrons does not involved. Okay, then ionic bond. In this ionic bond, what is ionic bond and what are the factors favorable for the formation of ionic bond we discussed. And next goes to covalent bond. What is the covalent bond and related examples. And next goes to coordinate bond. What is coordinate bond and related examples we discussed. And next goes to hydrogen bond. What is a hydrogen bond? What is a hydrogen bond and types of hydrogen bonds? Those are intermolecular hydrogen bond and intramolecular hydrogen bond, and also discuss the corresponding examples. Next goes to VBT. VBT is nothing but valence bond theory. It explains the formation of covalent bond by overlapping of orbitals. Yes. The VBT is explain the formation of covalent bond by overlapping of orbitals. Next, we discuss the VSEPR theory. VSEPR is nothing but valence shell electron pair repulsion theory. Don't call Vesper because of there is no spelling Vesper. Vesper means VES. Yes, but there is no VES spelling. It is the VSEPR. That means valence shell electron repulsion theory. In this topic, we discuss the postulates of VSEPR theory and I give the related tables. And next goes to we discuss the hybridization. What is the hybridization and types of hybridizations? Those are sp hybridization, sp2, sp3, sp3d, and sp3d2 and related examples. Next, just now we discussed the mot and molecular orbital theory. Okay, in this molecular orbital theory, it is explain the bond order and used to explain the magnetic nature and corresponding MOE molecules of H2, He2, and O2 and N2. Okay, and also we discussed the bond parameters. The bond parameters are bond length, bond order, bond angle, and bond enthalpy. So now important questions related to this chapter. Important questions related to these chapters. Those are, what do you understand by hybridization? Explain the types of hybridization involving s and p orbitals. Next question, give an account of VSEPR theory and its applications. Next, give the molecular orbital energy diagram of N2 and O2. Then calculate the respective bond order and write the magnetic nature of N2 and O2 molecules. Just now we discussed. Yes, yes. Next, explain the formation of ionic bond with a suitable examples and state the Poisson's rules and give suitable examples. And next goes to explain the hybridization involved in PCl5. And next, explain the hybridization involved in SF6 molecule. Next, explain the formation of coordinate bond. One example. And what is the hydrogen bond? And explain the different types of hydrogen bonds with examples. And next question, even though both NF3 are pyramidal, NH3 has higher dipole moment compared to NF3. Why? And next, explain why BeF2 molecule has zero dipole moment, although the BeF bonds are polar. These are most important questions regarding this chapter for IPE. Then we have time now. So now I will explain some simple methods for competitive purpose. Okay. Then now you keep these points in your mind, then it is easy to solve the problems in any competitive exams. It is belongs to hybridization topic. Then now number of electron pairs and hybridization. If the number of electron pair is 2, then that is the sp hybridization. The number of electron pairs 3, then that is sp2 hybridization. The number of electron pairs are 4, then that is the sp3 hybridization. If the number of electron pairs are 5, then that is the sp3d hybridization. If the number of electron pairs are 6, then that is the sp3d hybridization. These points you keep it in your mind. Next also, shape of molecule having only bond pairs. Okay, the number of bond pairs. If the number of bond pairs are 2, then the shape is linear. These are examples belongs to linear structure. And if the number of bond pairs are 3, then that shape is triangular. These are examples to belong this shape. And if the number of bond pairs are 4, then that structure is tetrahedral. And these are examples. And if the number of bond pairs are 5, then that shape is trigonal bipyramidal. And these are examples to the trigonal bipyramidal structure and shapes. Next, if the number of bond pairs are 6, then its shape is octahedral, and these are examples to this shape. If the number of bond pairs are 7, then its shape is pentagonal bipyramidal, and this is the examples to this pentagonal bipyramidal. Next goes to shape of molecules having bond pairs as well as lone pair electrons. Okay. So must and should you keep these three important tables for the competitive purpose only. Here, the bond pairs. If the bond pairs are 2 and lone pair is 1, that is the total electron pairs are 3. Then, if the total electron pairs are 3, out of these 3, 2 is bond pairs and 1 is lone pair, then that shape of the molecule is triangular, but actual shape is angular because of due to the VAC, according to VACPR theory. And total number of electron pairs are 4. Out of this total number of electron pairs, if 3 are bond pairs and 1 is lone pair, actually if the molecule has the total number of electron pair is 4, then its shape is tetrahedral, but it has one lone pair, then that shape is changes to pyramidal because of according to VACPR theory. Then same as well, the number of electron pairs are 4, then of these 4 number of electron pairs, 2 are bond pairs, and if it has 2 lone pairs, then its shape is angular. The next goes to, if the number of electron pairs are 5, then the shape is folded square. But if it has out of these 5 electron pairs, 4 are bond pairs, 1 is lone pair, then that shape is changes to seesaw structure. Next goes to, if the molecule has 5 electron pairs, then the shape is trigonal bipyramidal. But if it has 2 lone pairs, then the shape is changes to T shape. The next, if the molecule having the 5 electron pairs, then the shape is trigonal bipyramidal. Of these 5 electron pairs, if it has 3 lone pairs along with 2 bond pairs, then that shape is changes to linear according to VACPR theory. Then, if the molecule has 6 electron pairs, then that shape is octahedral. Of these 6 electron pairs, if it has one lone pair along with the 5 bond pairs, then the shape is changes to square pyramidal. The next goes to, if the molecule has electron pair 6, then the shape is octahedral. Of these 6 electrons, if it has 2 lone pairs along with 4 bond pairs, then the shape is changes to square planar according to VACPR theory. Then these points you keep in your mind for the competitive purpose. Then now, based on these points, how to identify the hybridization in given compounds in the competitive exams easily. Okay. Then this process is also used to calculate the number of lone pairs and as well as bond pairs. Okay. Now, hybridization is nothing but lone pairs and bond pairs. Okay. Then example, SO3 minus 2 ion. If SO3 minus 2 ion is given, then how to calculate the hybridization and lone pairs and bond pairs in this SO3 minus 2 ion easily. Okay. Then first of all, you select the central atom. Then in this SO3 minus 2 ion, the sulfur is the central atom because of it is a single atom and also it is belongs to less electronegative atom. So that it is considered as a central atom. Then now it is belongs to sixth group. The sulfur is belongs to sixth group. So now you will put the 6 electrons on its sulfur. Okay. Then next, after the sulfur is overlapping with the 3 oxygen atoms. Yes. Then here one oxygen atom is bonded with the bonded with the 2 electrons in this sulfur atom, each oxygen atom. Okay. Then each oxygen atom is bonded with the 2 electrons of the sulfur atom. So this is the one oxygen is bond with the 2 electrons, and this is also oxygen also bond the 2 electrons. Here also the oxygen is bonded with the 2 electrons of sulfur atom because of it has 3 oxygen atoms, and these 3 are bond pairs, and remaining this electron pair, this electron pair is a lone pair. Now the SO3 minus ion, it has 3 bond pairs and 1 lone pairs. Then total pairs are 4. Then hybridization is nothing but lone pairs and bond pairs. Okay, the total pairs are 4. Just now I give the one table. If the total number of electron pairs are 4, then that hybridization is sp3 hybridization. Then sp3 hybridization, according to VSEPR theory, the shape is pyramidal. This SO3 minus 2 ion structure. Next, let us take the example H2S. In this H2S, now we will take the central atom. Then this sulfur is the central atom and it is belongs to sixth group. So now we will put the 6 electrons in its sulfur atom, and this sulfur atom is overlapping with the 2 hydrogen atoms. In this 2 hydrogen atom, each hydrogen atom forms the only single bond with 1 electron of the sulfur atom. So now it has 2 hydrogens. So these 2 hydrogens forms the 2 single bonds with these 2 electrons of sulfur. Then these 2 are bond pairs. Okay, bond pairs are nothing but the electron pairs which are participate in bond formation, called the bond pairs. Okay, lone pairs are nothing but the electron pairs which are not participating in the bond formation are called lone pairs. Here these electrons are participating in the bond formation, but here these electrons are not participating in bond formation with any other atoms, so that these are lone pairs. Okay, these are lone pairs. So now H2S molecule, the bond pairs are 2 and lone pairs are 4. Total electron pairs are 4. If the total electron pairs are 4, then that molecule is exhibit the sp3 hybridization. Then sp3 hybridization shape is tetrahedral, but it has lone pairs, but it has 2 lone pairs. So that according to VSEPR theory, the shape is angular. Next, let us discuss example XeF2. Okay. Then in this XeF2, xenon is the central atom. Okay. Then it is belongs to 8th group element. So put the 8 electrons on the xenon central atom. And this xenon is overlapping with the 2 fluorine atoms. Okay. Then each fluorine is forms the one single bond. Because of these are fluorines are belongs to 7th A group elements. So all the 7th A group elements need only one electrons to get nearest electronic configuration, so that the fluorine is forms the only one single bond with this one electron of the xenons, and another fluorine is forms the single bond with this electron of the xenon. So these are bond pairs. The remaining are lone pairs. So now it has 2 bond pairs and 3 lone pairs. Now total pairs are 5. If the electron pairs are 5, then the hybridization is sp3d hybridization. Okay. Actually, the sp3d hybridization shape is trigonal bipyramidal. But here it has 3 lone pairs. That is the reason according to VSEPR theory, the shape is linear. Now test yourself question. Find out the hybridization of given compounds. This is a test yourself question. Try find out the hybridization of given compounds. First one, PO4 minus 3 ion, and B is I3 minus ion, and C is NO3 minus ion, and D is NH4 plus ion. The next goes to identification of types of hybridization in given compounds. How to identify the hybridization in given compounds? For example, this is the compound is given. Then here this carbon is exhibit the sp3 hybridization. It is in this also this carbon shows the sp2 hybridization. How to identify? If the actually the carbon forms the only 4 single bonds. Okay, carbon forms the only 4 single bonds. If the carbon has 4 single bonds, then that exhibit the sp3 hybridization. Okay. If the carbon has one double bond along with 3 single bonds, then that exhibit the sp2 hybridization. If the carbon has 2 double bonds along with 2 single bonds, then that carbon is exhibit the sp hybridization. Okay. Then here this carbon is exhibit the sp hybridization because of it has 2 double bonds along with 2 single bonds, so it exhibit the sp hybridization. And this carbon is also exhibit the sp hybridization because of it has 2 double bonds along with 2 single bonds. Same as well here also this carbon is exhibit the sp2 because of it has one double bond along with 3 single bonds. Here this carbon has 2 double bonds along with 2 single bonds. So it exhibit the sp hybridization. Then here also this carbon has one double bond along with 3 single bonds. So it is exhibit the sp2 hybridization. And test yourself question. Identify the hybridization of each carbon atom in following. Identify the hybridization of each carbon atom in the following. The next goes to how to identify the paramagnetic and diamagnetic species. How to identify the paramagnetic and diamagnetic species in given compounds in the competitive exams easily. Okay. Then here all odd electrons and 16 and 10 electrons. All odd electron 10 and 16 electron species will be paramagnetic in nature, and even number of electron species except 10 and 16 electrons. Even number of electron species except 10 and 16 electrons will be exhibit diamagnetic in nature. For example, here this is the lithium molecule. Okay. In this lithium, actually it is formed by the 2 lithium atoms. One lithium atomic number is 3 and another one is 3. So total here this lithium molecule has 6 electrons. Okay. 6 means it is the even number. Yes, it is the even number. So here all even number of electron species except 10 and 16 will be diamagnetic in nature. So lithium molecule has 6 electrons. So it is the even number. So it exhibits the diamagnetic nature. Next goes to N2 molecule. It is formed by the 2 nitrogen atoms. Then it has the nitrogen molecule has 14 electrons. It is also even number. So it is also exhibit the diamagnetic nature. The next goes to He2 plus ion. He2 plus ion. Actually, the He molecule is formed with the 2 helium atoms, and it has 4 electrons and it lost 1 electron because of it has 1 positive charge, so that it lost its 1 electron. Then now He2 plus ion has 3 electrons. Okay. So the 3 is the odd number. So here all odd electrons and 10 and 16 electron species will be paramagnetic. So here this 3 is the odd number. So this helium He2 plus ion is exhibit paramagnetic in nature. Next goes to O2 minus ion. This O2 minus ion has how many electrons? O2
Madam?
minus. Sir.
Kindly close the session, madam.
It's okay, sir. Okay. If you understood this, then you will try to solve this below question. Test yourself question. Which of the following species exhibit the diamagnetic behavior? Which of the following species exhibit the diamagnetic behavior? So, time is over. So, thank you, one and all. And once again, thanks to Secretary Sir and DS Deputy Secretary Sir and Coordinator Madam and my Principal Madam. Thank you, one and all. All the best, my dear first year students. Do hard work, get more marks, and bring the good name to our society. Thank you, one and all.
Thank you.